Okay, should be recording now. And with that, just a couple of things. The tests, 30 multiple choice questions, randomly chosen from a bank of questions. It's comprehensive. So this study guide, what I've done with this is it's just broken up by topic. With the test, it's going to be a 60-minute time limit. Closed notebook, internet, neighbor, everything. So be honest. And I would recommend when you're sitting down to take the final, make sure you have really good internet connection. You're somewhere quiet where you're not going to have distractions or interruptions that could pull you away. Just to make sure you have plenty of time and focus to take care of this and work through this. So with that, we'll get started. So we're going to start with oldest. We're going to go back to the beginning. And just 1 second, I'm going to mute this. All right, so we'll start now with plate tectonics, and then we'll work our way forward. So the first thing is, you guys remember what the different types of plate boundaries are? There's 3 of them. No, I can't hear Jazz. Okay, let's see. I don't know. Yeah, we've got convergent. And Caleb, I wasn't able to hear you. Was everyone else able to hear him? Sounds like I might be able to hear you now. Try talking again, Caleb. All right. Well, Caleb's doing that. I think your microphone might be sorted. I can hear it moving around now. But yeah, we've got convergent and divergent. And what's the third type of boundary? Yeah, we got transform. Perfect. Now, who remembers the direction of movement for both the convergent, divergent, and transform plate boundaries?
It goes through the cracks, it goes up like that.
Anybody? Okay, which one is where they're colliding together? Who remembers that? Yeah, good job, Karen. It's convergent. Okay, so which is the one, someone else, which is the one that's pulling apart? Anyone else? Give it a shot. Okay, so divergent is when they pull apart. Now, if you remember, you can look at me in the picture. So convergent plate boundaries, you got your 2 plates, they're moving together, one goes underneath, and they converge together. It's a good way to think about it. Divergent, they're pulling apart, they're diverging away from each other, okay? So remember that, and then the last one, transform. Who remembers the direction of movement along a transform plate boundary? Yeah, so not slides under each other. That's the convergent. Remember, the convergent sliding underneath. But they do slide against each other, but they slide side by side. Okay? So, yeah, exactly. Perfect, Danny. It's just moving side by side like this. Okay, so remember those. Now, which type of plate boundary produces the big mountain ranges? Who remembers that?
Convergent?
Yeah, perfect. Yeah, got it. And your microphone's working good. So, yeah, convergent plate boundaries are what produce these big mountain ranges. So, who can think, so Caleb, where's an example of a big mountain range produced by a convergent plate boundary? Can you think of any?
A mountain, that is?
Like a big mountain range.
Isn't I forgot.
You're fine. Anybody else want to help him?
I'm already, Mom.
Yeah, the Himalayas. So the Himalayas is being produced by India crashing into Asia, and that's creating these big mountains. Perfect. What are some other features that we see? You're fine. What are some other features that we see that form at convergent plate boundaries? So we get big mountain ranges when we have continental crusts and oceanic crust colliding, or continental and continental collision. But what are some other features, for example, when two ocean crusts collide? You guys remember that from the reading? I know this has been a while. So that's one thing. You'll get volcanoes, especially along ocean continental, and that's where they get it. So hotspots, though, don't come from that. We don't quite know why hotspots form, but they don't form along plate boundaries.
Oceanic trenches.
That's right, Caleb. Perfect. You get the big trenches. So that's the Marianas, like the Marianas Trench over in the Marianas of the Pacific. That's the deepest part of the ocean. And basically what happens, if you look at my hands, it starts subducting under, and it'll pull a little bit this top slab down, and it'll make a little trench. And these get really deep. So perfect. So we've got volcanoes, such as are found in the Cascade Mountains up in Western Oregon and Washington, where we've got the Juan de Fuca plate subducting underneath the North American plate. You've got large mountain ranges like the Himalayas, and then you get oceanic trenches like what Caleb just mentioned with the Marianas Trench. Very good. Okay, any questions on plate tectonics? That's the big stuff I wanted to get. Okay, I think we're okay. So if we have any questions at any point during this, just shoot it out in the chat. Just unmute yourself and say, hey, Brother North, I've got a quick question, and we can go back and we can address it. So we'll move on now to earthquakes. So it's really common that I see that students confuse earthquakes and faults and earthquakes with plate boundaries. Remember, faults have their own names, but they'll have similar movements to plate boundaries. So what are the different types of faults that we see? Not plate boundaries, but faults.
I know normal fault is one.
Yeah, perfect. We've got a normal fault. So what direction of movement is the normal fault?
Isn't it like where the one like falls down?
Yeah, exactly. A good way to think of it, and I wish I had a whiteboard, but you've got like this, right? And it slides down. This top part slides down like you were saying, Caleb. An easy way to remember it is this is the hanging wall, and this is the foot wall. And to make that simple, if you drill a mine shaft through it, the hanging wall, which is on the top, is where you would hang from. The foot wall, which is on the bottom, is where your feet would stand. Okay, that's the way geologists use it. This is the hanging wall, this is the foot wall. In a normal fault, the hanging wall goes down. So the part you would put your hands on hangs down. Okay? Perfect. So what's another type of fault?
In the chat, they both goes up.
Yeah, there's the one that goes up. Who can remember what that's called?
Go with thrust.
Thrust, yeah. That's one way. There's a thrust, which is a type of these faults, and you wouldn't get it wrong by putting thrust. Now, you said it moves the opposite direction, right? So the hanging wall goes up relative to the foot wall. The top goes up. So an easy way to remember the name is it's the reverse of a normal fault. It's a reverse fault, what we call it. So it's the reverse of a normal fault. Okay, so that's an easy way to remember that, is that a reverse fault, the hanging wall or the up top part goes up, and it's the reverse of a normal fault. Okay? And then, perfect, Janet, we've got a strike slip. Who remembers the motion of a strike slip fault? Perfect, great, Janet. It's side to side. So if you've got your two sides like this, it's moving like this. You know, it's kind of moving this direction. So can anyone think of an example of a strike slip fault?
I remember that one in California. I remember seeing.
Yeah, that's right. The San Andreas. Perfect, Danny and Caleb. The San Andreas fault is an example of a big strike slip fault. Now, an example of a big normal fault would be the fault, if for those of you who are familiar with Utah, the fault that runs along the Wasatch Front, called the Wasatch Fault. And then the example of a big thrust fault is one I can't think of. I don't know of any like specific named ones. I know where they form. But now that we've talked about those different types of faults, which type of fault is usually found along the base of mountains in the western United States? Can anyone think of one? What they are? At the base of mountains along the western United States. This is kind of a harder question.
Isn't it just a normal fault?
Yeah, exactly, Caleb. It's a normal fault. Perfect. So think of it this way. Initially, it was like this. And then you had your first event. And the main level, for example, we'll use Utah. Oops, sorry, my son just bumped me. The main level, the base, the valley fell down. And over time, it just slid down, and it leaves these peaks that go up a little bit, and that helps make the mountains a little bigger. It's not the only way mountains are formed, and along the base of them. And actually, thrust faults are one of the major mountain building components, but they help in building the mountains in the western United States. It's not that way over in like the Himalayas or whatever, and that's something you guys don't need to worry about. That's something called basin and range extension, so don't worry about it. Okay. Who remembers where the largest earthquakes happened? Or excuse me, what type of plate boundary the largest earthquakes happen at? Not quite strike slip. It's actually convergent. You're right, Karen. It's these convergent plate boundaries. Strike slip have big earthquakes. They do. But, you know, like this one, for example, we'll use Ridgecrest, the Ridgecrest earthquake. That was along a strike slip fault, right? It wasn't actually on the San Andreas, but it was on a fault parallel to the San Andreas. So a strike slip fault, and it was a magnitude 7. The second one was a magnitude 7.0. Oh, you feel it, Danny? Oh, I was actually there too. I was over in Tehachapi, if you know where that is. So it's a magnitude 7.0 earthquake happened along the Ridgecrest earthquake, or the Ridgecrest fault, basically, right? So that's a pretty big one. It's actually a very large earthquake. I don't remember what the 1989 World Series earthquake was, but I believe it was a 6.9 to a 7.1. So roughly the same size. These are big earthquakes, and they, make history. But a convergent earthquake, I'll give you an example of a fairly standard size earthquake along, well, not standard, but a fairly big earthquake that happened along the a convergent plate boundary was the Tohoku 2011 earthquake in Japan. That's the one that caused the meltdown of the reactors at the Fukushima nuclear plant. Now that earthquake was a magnitude 9.0. That's right, it created the tsunamis. That was a magnitude 9.0 earthquake. And if you remember, the magnitudes are logarithmic, which means that a 7.0 is 10 times bigger than a 6.0. And an 8.0 is 10 times bigger than a 7.0. And a 9.0 is 10 times bigger than an 8.0. So what that means is that the earthquake that happened in Japan was 100 times bigger than this earthquake that happened in Ridgecrest, California. So the big earthquakes happen at these convergent plate boundaries. And an easy way to remember that is the biggest earthquakes happen in Japan. So, and Japan is on a convergent plate boundary. So that's I think that's how I remember it. I think that's a good way that worked for me when I took this class years ago. So I think hopefully it helps you guys. All right. Any questions on that? Okay. If not, or if you think of one in a few seconds, just shout out and we'll go back. Okay, so now also, let's see. Who can explain epicenter versus a hypocenter on an earthquake? And while you do that, we're going to pull up a thing.
Can't remember which one it is, but
Go down.
I
Okay, take a shot at it, Caleb. It sounded like you were about to give it a shot.
The hypocenter is where the earthquake initially happened underground, and then the epicenter is where it happened directly above it.
Perfect, very good. So we'll go up to this figure right here. We got your epicenter, which is where it broke. That's the point that the ground broke and the slip started. The epicenter is the geographic location on the surface directly above that. So if you look at this figure, that doesn't mean that's where it's going to break. So for example, you know, sometimes we see on sides of, you see where an earthquake happens and a crack opens on the ground, or there's a kind of a, we call it a scarp, but basically this ridge that forms where the earthquake kind of broke the ground, that is typically not your epicenter, because again, remember the epicenter is directly over the hypocenter, which is where the break began. So if you look at this image here, you've got this line representing your fault, and it broke down here first, but it didn't expose on the surface until over here. So just remember your epicenter is directly over the hypocenter, and the hypocenter is where the break started. Does that make sense to everybody? Okay. We'll go to this. All right. Very good. Okay, now what we'll do is we'll go back here. Who remembers what liquefaction is? Who can explain liquefaction? And let's do someone that hasn't answered yet. And I'll put up an image so you can see liquefaction again. This is a beautiful, that's an okay example. An okay example of liquefaction. Yeah, this is a great example of liquefaction right here. So who can explain liquefaction for us that has not yet answered a question? And you can use this picture I've got up here for you to help you describe it. Or better yet, there you go. This will help, this figure right here. So who can explain to me this figure? I'll give you guys a couple of minutes to read it, and for those typing, we're using chat to type it. Actually, it might be that pretty much everyone's answered something. I guess everyone has answered something. Great. So Danny's saying the soil gets saturated. And so what does this saturation cause to happen? I mean, in liquefaction, what happens when the soil gets saturated? And anyone can answer that part. Perfect. It acts like a liquid. So what happens is, right, when we go back to this car, it's sitting on solid ground, but then what happens is the soil gets saturated with the liquid, with water and different things, fluids, and then that car automatically sinks in because it starts to behave like a liquid. Now, what soils are prone, or I gave you a hint here, but what is prone to liquefaction? Clays and sands, yeah, sandy materials. Anything that we can get water in between the individual grains and particles to saturate them and float them apart a little bit is going to make it prone to liquefaction in the case of an earthquake. Also areas, if they have a high water table, that's another part that really helps this out. So in a city, where would be some zones? If you're in a city on the coast, where would somewhere that in the city that would be prone to liquefaction? See if you guys remember back to some of the readings in the case studies. Yeah, parts that are filled in, perfect. So that's like these areas. So if you think about, if you guys remember the, I believe it was the Kobe, Japan, and you guys actually looked at this on your guided labs, if you remember, that there were parts of these inlets and bays, along the ocean, where they actually brought sand in and made artificial land so that they could expand the city. Well, these areas are just sand and clays. So what happens when shaking starts to occur? Water gets in there and you get severe liquefaction. Very good. Okay, I think that's good for that. Okay. Okay, so the next one I'm going to ask question I want to go over are, where can earthquakes happen in the U.S.? Where are some areas that would be prone to earthquakes other than California in the United States? Make you guys think a little bit more. Yeah, Alaska is. Why is Alaska? Why would Alaska be prone to that, Dan? Anywhere there's a fault, that's a safe answer. Good job, Karen. But where would those faults be? So it's on a fault, but there's more to it. There's more to it. Not quite. Coastlines don't always mean that. So for example, the coast of Maine is not prone to earthquakes. And it has to do with something we already talked about, plate boundaries. I'll give you a hint there. So the big thing that it has to do is they're near plate boundaries. So Alaska is near a plate boundary. It's on a subduction zone. It's on a convergent plate boundary. So that area is very prone to earthquakes. That's why California is very prone. It's along a plate boundary. But there are some instances like New Madrid that are prone to earthquakes that are not near a plate boundary. And that has to do with other things like hotspots and failed rift zones and things like that. So why would somewhere like Maine not be prone to earthquakes? Let's see if you guys remember these maps. It's a map of all the plate boundaries, but what do you think?
Is it because that doesn't do around that divergent?
Say that one more time.
Because it's like by that divergent plate boundary.
Yeah, and the divergent plate boundary is actually a long ways away. As a matter of fact, let's go look at this here. Boundaries. And let's go to images. So when we look, here's Maine right here. The closest plate boundary is all the way out here. So this is what we call passive margin. There's no earthquakes happening here. But right here, all along the western coast of the United States, of North America, you got all these plate boundaries. So they're incredibly prone to earthquakes. See, also, if you look at the Caribbean, lots of a plate boundary right there. South America, plate boundary. And then you come to the eastern margins of these areas of South America, North America, and there's not a plate boundary for thousands of miles in some instances, so they're not prone to earthquakes. Now, you get some things in here, you know, in the center, like Utah, that are prone to earthquakes, and that has to do with other things. You don't need to worry about that, and you won't be tested on that. But it is important to note you will get earthquakes on divergent plate boundaries. Just if it's on a divergent plate boundary, it'll still be prone to earthquakes. It's just going to be smaller earthquakes. So the Mid-Atlantic Ridge is always undergoing seismicity. It's always experiencing earthquakes. A good example of this is up in Iceland. Iceland is always having earthquakes. And it's just that it has a plate boundary there. And if you think about it, a plate boundary is where you have two plates moving, either side by side, one under the other, or apart. And anywhere you have these big plates, because again, look at the size of these plates. These things are moving in some cases up to millimeters to centimeters a year. I think the North American plate is about 1 to 2 centimeters a year. So if you think about that, in 1 year, the North American plate will have moved that much. It could have moved up to that much. So that means there's going to be earthquakes along these plate boundaries. Okay. Now, let's see. Let's go back to this. There we go. Okay, some things to know with case studies. I'm going to post more of those guides that I posted for test 3. I'm going to post more of those guides for the final exam for the other case studies so you guys can have those. So I would recommend going through those and looking at, particularly with the earthquakes on the earthquake section, what the 2 largest earthquakes on record are. We've already spoken about one of them. Which case study earthquake had the highest death toll, and where in the U.S. 3 large earthquakes happened in a short amount of time. So that's not the Ridgecrest. Ridgecrest only had 2, first off, and also the Ridgecrest earthquake was so recent we didn't have time to put any material together for the class. And then the last one was, where was the largest earthquake in European history? Let's see if you guys, anyone out of curiosity, remember what is the largest earthquake in European history? Not Greece. It was one of the case studies. See if you guys remember back that far to reading. Not Iceland. You guys are thinking of Himalaya, which was the volcano in Iceland. Close, Karen. You're so close. It's one country over. And it's not France. See if anyone can get that from that hint. Now we've gone too many countries over. We're going the wrong way. It's Portugal. It's the Lisbon, Portugal earthquake in the 1700s. So it's the Lisbon, Portugal earthquake. So I'll post that. You guys can go through that, look through that. We're not really going to go over the case studies on this. You have this to go through. And then I'm going to post those documents for the case studies. If you go through those documents, if you go through those documents, it'll have everything on them. Yeah, so 1700s in Italy was the largest, or in Italy, sorry, I just read, I looked at the chat and saw Italy, and for whatever reason, that's what came out. So the 1700 it was like 1755, I believe, earthquake in Lisbon, Portugal. So about 300 years ago. Okay, and know what the impacts were for these. So we'll hop on over to volcanoes. So let's see, where do we want to start with volcanoes? What are the different types of volcanoes? See what you guys remember. Sorry. Yes, you've got a stratovolcano. And Karen, how do we identify stratovolcanoes? Not sure. Anyone else? How do we? So Mount St. Helens is a great example of a stratovolcano. Perfect. So Danny, how do we what from basic thinking about Mount St. Helens, how do we identify a stratovolcano or a stratocone volcano? Huh? Yeah, blows the top, puts all kind of stuff into the atmosphere. Very good. That's part of it. I'll give you a hint, a simple answer too. There's a really easy one, and I'm probably asking too simple of a question. Types of volcanoes. Okay, images. So we've got this right here, types of volcanoes. Go. See if this loads. Okay, we've got this beautiful figure right here. Hopefully we can get it big so everyone can, it's easier to see. Nope, not gonna work. Okay, we're gonna do it this way. So yeah, they don't put us out as much lava really. But look at this, we've got right here a composite volcano, which is also a stratovolcano. And the big thing with the stratovolcano is look at the shape. It's the big, steep-sided, pointy mountains. So think about Mount St. Helens beforehand. Think about Mount Hood over by Portland, Mount Rainier. We'll take a look at a good picture of one, just to get a good sense of it. Oh, I love this one. Perfect. Mount Fuji. Mount Fuji is beautiful. It's a perfect example of it. Just that big triangle, the big traditional looking volcano that everybody thinks of. That is a stratovolcano. It's a big mountain, big and tall. It's got all the glaciers and the snow up on the peaks on the top. And when they blow up, oh, it's quite exciting. Well, you going to bed, bud? You going to bed? All right, just a second, everybody. Sorry, I had to do bedtime kisses. And my oldest says he will see you tomorrow, but I don't know about that. So if you watch it tomorrow, I guess you will see him tomorrow. So when they erupt, these big stratovolcanoes, oh, let's put it here. Okay, when they erupt, they are the type that are like Mount St. Helens, and they blow the tops completely off, very explosive. Have the big pyroclastic flows, the lahars. These are the ones that kill the most people. Very good. Okay, so what other type of volcano do we have? And we'll go back and look at it. Perfect, we got a shield volcano. And just based off of that name, perfect, Hawaii. So what do shield volcanoes, what are some of the distinguishing traits that we can use to identify a shield volcano? Yeah, wide, far spread, beautiful. That is exactly right. And look at this image. Do they have a good one? Composite caldera. This is I don't like their image of a shield volcano. It's hard to gather it, but we'll do this. We'll come over here and we'll look at a shield volcano. So they're really broad, shaped like a shield roughly. Oh, I put shield. Helps if I put volcano in there. So this is a beautiful shield volcano. And it's a relatively small one, but you can see very, very gentle slopes arcing up and this nice rounded feature. This is like what Hawaii looks like. Mauna Loa, Mauna Kea are just giant shield volcanoes like this. And just the very peaks peak out over the top of the ocean. and that's where we got the Hawaiian Islands. As a matter of fact, the largest mountain in the world is a shield volcano, and that is not Mount Everest. That is Mauna Kea or Mauna Loa, and that is it is like doubled the size of not doubled, but it's pretty close. I think doubled the size of Mount Everest when you go from the very base at the bottom of the ocean to the top of the peak. So they're very big. What characterizes their eruptions? What are their eruptions like? That is a great question. So the question is, why does one become a shield? Basically, how do you get a shield volcano versus a stratovolcano? And that's a fantastic question. And that has to do with the magma. As a matter of fact, we're going to go back to natural disasters here. I'm going to stop the screen share for a second, guys. And I'm going to hop over and pull something up. Announcements. Search. And, okay. 3. Okay. Okay, I'm just pulling up a PowerPoint. Give me a second. But it takes me a minute to get some of these up, so bear with me. Ugh, hold on. Okay, so while I talk about this, I should have pulled this up a few minutes ago. Week 5, 6, here we go. While that's opening, it's just opening right now. I'm pulling up a PowerPoint. Okay, so it has to do with essentially the composition of the magma. And who remembers the difference between lava and magma?
Lava is, lava's above me.
Exactly. So magma's underground, lava's on the outside. It's the same thing, it's just where it's located. And so it has to do with the composition of the magma while it's in the subsurface, okay? And basically, let's get this up. You can get some things that make a magma more viscous, and we'll talk about that real quick. Let me go to a particular slide if this is ever opening. Okay, ignore that. The presentation gallery. Sorry, my computer is really old and really slow. There we go. Okay, so maybe we'll get there. Okay, perfect. Okay. Okay. Now we're gonna go here. Okay. So we're gonna look at this presentation now. This is okay. So right here, looking volcano basics. Okay. It has to do with the second bullet point. Why are volcanic gases important with regards to eruptions? And and then also the chemistry of them, of the magma, as well as what's called the viscosity of the magma, this last bullet point here. So what it has to do with is your magma, if you get more what's called silica in it, it makes a more felsic magma. And basically what that means is when you get these typically along subduction zones, this is where your composite volcanoes form along subduction zones, and they pick up a lot of quartz and other minerals from the crust as it's being subducted underneath. So remember, on your subduction zone, you've got this slab right here going underneath. And what happens is it starts to melt down here. And as it melts, it brings stuff up and it incorporates a lot of old minerals, and it raises that were already formed in the crust, and it raises the silica content in the magma. And what this does is it means there's more gas. Sorry, I gotta open the chat. I see chat. All right. Yeah, silica, they do make glass out of silica. So it raises the silica content. It makes more gas in the lava, or the magma, excuse me, and which the gas comes from the water, from the subducting of the slab, and then it makes it more viscous. Who remembers what viscosity is?
The thickness of
That's
the
right.
lava.
So if it's more viscous, it's thicker. If it's less viscous, it's thinner. Okay, it's kind of like the syrupiness. It's the resistivity to flow. It's more, and so what happens is if you think about a lava chamber, if you think about a magma chamber forming, it's underground and it's got all this, it's this confined space, almost like a can of soda. And what happens if you start making a lot of gases and it's really thick and it's really thick? What's that going to do to the explosion? Because remember, it's all contained in this chamber.
I remember like it contains it, kind of like that's what the Hawaii means. It just makes it so it oozes out. Is that right?
No, not quite. So think about like what Karen said. It makes it more explosive. So think if you have your can of soda and you shake it really hard for a couple of seconds, what happens when you pop the top? It explodes everywhere, right? Well, what happens with these stratovolcanoes is it's got all this stuff underneath. It shakes. It's being shaken, and eventually it gets so much pressure in it, a little earthquake or whatever pops the top and makes this explosive eruption. Whereas these Hawaiian volcanoes, these big shield volcanoes, typically form from hot spots, and it's just this hot mantle plume that rises and melts through the subsurface. And think of it as, like you were saying, Caleb, it kind of oozes out this magma, and it just builds these gentle, gradual slopes up. It's not highly explosive. It doesn't have a lot of silica. Doesn't have a lot of gases in it. It's not really thick. And so it just oozes out, and it just builds and builds and builds this big shield type volcano. Does that kind of make sense, Danny, how those are formed and what controls the difference?
So I was just wondering, so high viscosity is more explosive?
It's, yeah. Because think about it. It's harder to move, so it requires more pressure to explode. Yeah, perfect, Danny. So the lava in Hawaii is significantly less viscous than what you would get out of a magma chamber for Mount St. Helens or Mount Hood or Mount Rainier.
I had them backwards.
Yeah, it's easy to do. It actually feels a little counterintuitive. That I remember when I was first learning about viscosity, it felt like less viscous should be thicker and higher viscosity should be thinner. But it's actually the reverse of that. The more viscous, the thicker. The less viscous, the thinner.
Okay.
Great. Okay, so we'll just keep going through a little bit of this for a few minutes. I'm also going to post this for you guys. Know the rock types: rhyolite, andesite, basalt. where they come from. Remember, rhyolite and andesite kind of come from your composite volcanoes, and basalt is from your shield volcanoes. And remember, composite volcanoes are your stratovolcanoes, okay? I'm actually going to hop back over to this. Let me stop the share and share this. Okay. And let's go to this. Next, we have the cinder cone volcanoes. They look similar to a stratovolcano, but they're significantly smaller. So here's a beautiful picture of a cinder cone volcano, these guys right here. And a cinder cone volcano can be, you know, hundreds of feet tall to a few thousand feet tall, whereas your stratovolcano is going to be, you know, Mount St. Helens, Mount Hood, 12,000, 13, 14, 15,000 feet tall. So scale is different, for one. Number two, it's going to be composed mostly of ashes and cinders, because look, here's one erupting right here. It's beautiful. It's spraying all of the lava into the air, and it comes down and forms these beautiful cinders and ash and whatnot. So that's kind of the distinction on those. Caldera forming, these are the ones where they collapse in and they have the big caldera in the center. This would be like Crater Lake. Oftentimes a caldera volcano will have started out maybe as a composite volcano, and then the top is collapsed in. So this would be like Anak Krakatau, which is the volcano that formed in Krakatoa after Krakatoa formed. That little guy in there, it's kind of that. Or, well, I guess Krakatoa in general. Anak Krakatau is more like a cinder cone in the middle. You've got the fissure volcanoes. These are where the fissures open up. These can happen on your shield volcano. So like the eruption that happened just not this summer, but last summer in Hawaii, those fissure eruptions, those would be like a fissure volcano. So I think that's good for that. So we will go now back to this one. Okay, where do volcanoes occur? Name some places. See if anyone can think of any. We talked about some of them. So let's see if we can remember what we talked about. All right, we've got one new message here. Cascade Range, beautiful, Karen. Why? Perfect, and you got it. On a convergent plate boundary. So along convergent plate boundaries, we'll get the big stratovolcanoes. Great. Where do we see shield volcanoes commonly? Yeah, hotspots, perfect. And there's one last trick one, actually. Divergent plate boundaries also form volcanoes. So if you think about it, the mid-oceanic ridge, that ridge along the center of the Atlantic where it's spreading apart, there's like tons of volcanoes along there, just as that have the lava spewing out. So basically, along plate boundaries, we get volcanoes, and except plate boundaries. So divergent and convergent plate boundaries, we would get volcanoes. We don't get them along transform boundaries, but along divergent and convergent, and then hot spots. So those are the three places we get volcanoes. Beautiful. Yeah, they're underwater, typically. Very good. Sometimes they're not. It's not truly divergent plate boundary, but it's starting to form a divergent plate boundary in Ethiopia. And there's actually just this random lake of lava in the middle of the desert. That is an example of a pseudo-divergent plate boundary forming with a volcano on the surface. Really cool. Okay, as a matter of fact, one of the BYU professors goes there every year. That's the lady I did my master's degree under. Not every year, but she goes there frequently. Okay, what is a hotspot? We talked about it, but who can re-describe a hotspot for me? Yeah, that's fine, Karen. Go ahead and take off. I will have this posted tonight. I'm going to shoot for getting it posted tonight. It'll be a little bit because it takes me time to upload it. So let's look at an image of a hotspot and I'll show you.
Aren't they just randomly placed like all over?
Yeah. Gotta do geology. They are kind of randomly placed. We don't really know why they're forming, but this is a good image of one right here. So you've got this mantle plume. Basically, it's just this hot upwelling of material that rises to the surface and it melts through the upper crust, the lithosphere, so this crust right here, and forms these volcanoes. This is an example of the Hawaiian hotspot. There's another famous hotspot. I see if you guys can remember. It was mentioned in your reading. Where is there another famous hotspot in the world? There's another good one for you. Yeah, Yellowstone. Perfect. So Yellowstone is another hotspot on the Earth that we know of, and besides the Hawaiian hotspot. Very good. Okay, so we'll hop over back to this. What is the biggest? Okay, what is the biggest volcano on Earth? Yeah, we'll ask that. What is the biggest volcano on Earth? See if you guys can get it. So we're talking, and yeah, a shield volcano is one of them. But what is the name of it? Mount Fuji? No, I'll give you a hint. It's in the chat. Not Kilauea. It's Mauna Loa. Mauna Loa. Because remember, Mauna Loa is the big mountain. Kilauea is kind of on the side on it. It's like a shield volcano on a shield volcano. How about that? But Mauna Loa is the largest volcano. There is one actual volcano that is technically bigger in the sense of eruptive power. So who knows what the most eruptively powerful volcano is that we know of? It actually does not have the largest eruption of the past that we know of, but it is currently the largest active in eruptive power. I'll give you a hint here. Okay, there's the hint in the chat.
Oh, is it like Yellowstone?
Yeah, Yellowstone actually. Yellowstone is the current volcano that we know is still active that has the greatest eruptive power. So, volcanic eruptive index. Now let's take a look at this image here. Look at these. Here is this beautiful figure here showing eruptive power. We've got right here Mount St. Helens, which we know is a huge one. We've got Rainier, which was erupted 250 BC. So these are some big eruptions we're looking at here that we can comprehend, you know, with St. Helens, Pinatubo. Now there's Yellowstone here, which is a big one. Then there's Toba, which is a totally different one, a totally different supervolcano. But this Wawa Springs is actually is a Yellowstone eruption. So this is the size, eruptive power, an 8, of the Wawa Springs eruption of the Yellowstone supervolcano. So it gives you an idea of how big that volcano is. All right. Now, so we talked about what makes eruptions more explosive than the others. Remember, that's viscosity, your gas, and just kind of the silica content. And then with this one, what is the, all right, perfect, Janet. We'll have this posted for you so you can finish. What is the greatest threat if Mount Rainier, if it erupts? Let's see if you guys remember. Think back to the guided labs and the city of Orting, Washington. Lahars, perfect. Sorry, it took me a second to see that in the chat. Lahars are the greatest threat. Okay, and then this one, case study. A year without a summer. Know that. Know what caused the Mount St. Helens eruption, the volcano that buried Pompeii, and which volcano may have begun the legend of Atlantis. I'm going to post that document for you guys tonight that you can use to study. Landslides. Let's see. I'm going to say, are there any questions on landslides? We just went over this Saturday. But are there any immediate questions on landslides? Otherwise, I think landslides and tornado and floods we'll hold off on for the most part, because if people have to leave, if everybody has to leave, I want to at least get through everything. So if you don't have any questions, I just refer you to the video posted from Saturday for the review, a really good review on landslides and floods. But any questions? All right. We'll hop over to hurricanes. Okay, where do hurricanes get their energy? Who remembers? Warm air rising, warm, moist air rising. Perfect. So you get that rising of the warm air, you get the circulation starting to happen, and it just is like feeding gas into these big supercells. It just gasses these things up and gets them moving. So that's why, for example, Dorian came in and it hit those warm waters of the Bahamas and the Caribbean, and it just like maxed the thing out at a category 5, making it the largest hurricane we'd ever seen. It just hit those nice warm waters and it just fed the storm. Perfect. So who remembers what some of the requirements are for a hurricane? We're going to go here too. For the formation of a hurricane, we're going to go all the way down. I'm pulling that up too for you guys. We'll go through some PowerPoints with this. Oh, that's tornadoes. I forgot. Hurricanes are the second half. But what are some of the things you need that you guys can think of? So we know we have to have warm air rising. What else do we need? So the first thing we need is this right here. We need to already have a storm. It can be just a normal thunderstorm or a squall in place. They can start to suck up this warm air, this warm, moist air, and start building out to get circulation. So we need to have that. And I guess it's the other presentation that has more. All right, sorry guys, I gotta move a bunch of stuff. Yeah, we got to have that circulation of the cool air filling in. Opening up. Perfect. So you also have to have, so we've got the disturbance, right? That's, you already got to have that storm in place. It has to be near the equator, just north of it. Remember that location. It's got to be, you're not going to get a hurricane up in the North Atlantic up by, Norway. That just doesn't happen. You don't have the right settings there. And then you have to have little change in wind speed and or direction with height. So in other words, what it's saying is all the wind should be going in the same direction and same speed all the way up the atmosphere. You got to have the warm seas, you got to have an unstable atmosphere, and that just means temperature goes down as you go up, temperature variation. And then you have to have high atmospheric moisture content. So it's got to be humid. Now, why those last two? That might not make sense. Why does it have to have cool up above and warm down below? And it has to do with this warm air rising. Yeah, it is kind of interesting that they start so far off, isn't it? Off the coast of Africa, where those conditions are real good. So with relation to the last two, number 5 and 6, unstable atmosphere, so the temperature gradient, and then the high moisture, high humidity, is that when you have cold air up above and warm air beneath, what does hot air like to do? Does it like to stay underneath, or does it like to rise? Yeah, it likes to rise. So it's going to rise, and that cold air is going to sink and then fill that spot. So you get that circulation, remember, that we need for the hurricanes, or that we saw here, where we've got, oh, where's that figure? Maybe it was on the other side, but you can kind of see it here where you've got the warm air rising, cool air comes down and fills in and heats up. So we have to have that to get that warm air rising and cooling effect. Good. Okay, what is the most dangerous and deadliest part of a hurricane? See if you guys remember that. And why is it the eye, Danny? Why is the eye so dangerous? Okay, let's go. We're gonna look at a chart in a second, but can anyone have a guess? What hits the coast when the eye makes landfall? Might be fishing a little too deep here. That's right, the storm surge hits. And we're gonna watch a quick video on storm surge. Okay, weather.
Continues to close in on the southeast United States, and it will bring with it the hazards of damaging wind and also the potential for significant storm surge flooding. One place that we know that is really vulnerable to storm surge flooding, that's Charleston, South Carolina. There could be as much as 3 feet of water rise above normally dry ground in and around the Charleston area. Let me show you what that looks like. Here, for example, imagine 3 feet of water comes in. Well, when that happens, it's too late to evacuate. 3 feet of water can knock you off your feet and also potentially flood the first floors of homes and businesses. It is also possible, depending on the track of the area, that we could see water rises even higher than that, maybe as much as 6 feet. That's above my head. Now, that is truly a life-threatening scenario where you absolutely have to be on the second floor of a building or a residence in order to survive this kind of outcome. Now, again, remember, Hurricane Dorian's forecast is unknown. Stay tuned for the latest forecast from the National Hurricane Center and from the Weather Channel.
That's a great one. It gives a good example of a storm surge. Now, I want to show you one more.
Dangerous Hurricane Michael continues to close in along the northern Gulf Coast. We do expect life-threatening and catastrophic storm surge flooding along with it. Now let's use these maps to show you how much water rise above normally dry ground you should prepare for. These maps made by the National Hurricane Center give us almost a block-by-block assessment of how much flooding to expect. For example, let's zoom in on Panama City Beach, a very popular area of the Florida coast. These areas in yellow, up to 6 feet of flooding above normally dry ground. This is going to flood businesses and homes, and it's not just going to be at the beaches, it's going to be inland as well. Let's go down the beach farther to areas near, for example, Port St. Joe. This is a very vulnerable area of the Florida coastline to storm surge flooding. We do expect significant flooding there downtown as well, in areas in yellow and orange, up to 6 and even 9 feet of flooding above normally dry ground. So what does that look like? I want to show you. Imagine this. Imagine 3 feet of storm surge right here. Now, if this amount of water catches you by surprise, it's too late to evacuate. Cars are floating around and floating away. There's large objects in here that can knock things down with a battering ram-like force. Now, there's no way, again, to evacuate with this kind of storm surge. But we know there's going to be places with more than 3 feet. Imagine 6 feet of storm surge. Now, this completely floods out the first floors of homes and businesses, and the only way to escape that is to move to the higher floor of a building. Now, unfortunately, there are going to be places that get more than 6 feet of storm surge flooding. Imagine this, 9 feet and even beyond of flooding, of inundation. This is practically not survivable. So please follow the advice of your local officials when they ask you to evacuate. And if you have any questions about what evacuation zone you're in, if you need to go and or where you need to go to floridadisaster.org. And by
now, this may seem extreme, this time, to talk about it, but it's not in fact. As a matter of fact, the largest storm surge I've ever 27 feet of water. That's 3 times taller than the static top of the street. Out so you guys could hear. All right. We'll see you later. So that may seem extreme here, but the largest storm surge we've recorded is 27 feet. So basically to the top of that tree. So the storm surge is incredibly dangerous. And that is what comes with the eye of the storm. And if you get caught in the storm surge, oftentimes there's not much they can do for you. Because 1, you're going to either drown, or 2, you will be taken out to sea. And one of the major things that one of the major rescue operations that happens after many hurricanes is actually the Coast Guard patrolling the oceans, picking people up sometimes 5-10 miles out to sea who have been washed out from their homes in the storm surge. So that's the deadliest part. Okay. Now, and oftentimes they will be picking survivors up, not just bodies, which is the crazy thing. People sitting on mattresses. So where do hurricanes occur in the United States? We kind of saw that with that figure, right? They go across the, this guy here. Oh, that's this one right here. Right here, this beautiful image right here. They start over here towards Africa, or excuse me, over here towards Africa, and they go across and they come up and they hit our south to southeast border, Florida, Louisiana, Georgia, Texas, the Carolinas. Those areas are the areas prone to hurricanes. And then this is the last one on hurricanes we want to go over, is where does the Saffir-Simpson scale measure wind speed and damage at landfall. So category 1, 74 to 95 mile per hour winds. So the ones on the west that are on the west coast, I'll show you this. Good question. Thank you for asking. Go back here. These guys over here are originating over here, kind of down by southern Mexico, but they don't ever really hit us. They go out and they just kind of peter out in the Pacific. The ones that more cause the damage are these typhoons that happen in the middle of the Pacific, come across, they'll hit Japan, they'll hit the Polynesian Islands, they'll hit over into China, East Asia. But these guys over here that start over here, they don't really too often hit up here. And when they come up here and hit up into California, they usually are tropical storms by that point. Okay. Okay. Talked about storm surge. Talked about scale. So you can see here, this is sustained wind speeds. Category 5, 155 miles per hour. Dorian was a Category 5, and it kind of just plopped itself down on the Bahamas for 2 days and just blew them away with massive storm surge. And these are catastrophic storms when they reach that size. Category 4s and 3s are still extremely dangerous storms. And even 2s and 1s can cause fatalities and deaths. So any hurricane is dangerous. And we need to make sure that one of the main things we need to remember is that it is important to make sure that we remember to obey and heed the warnings issued by the government and the National Weather Service. Okay, for the review for tornadoes, I just want to watch this real quick.
Save you money. Get coupon codes automatically applied to your shopping cart. Download Wikibuy for free. You're out on the highway on a collision course with a massive tornado. It's scary. It's bearing down on you. What should you do? It's not a good position to be in, and every situation will be different. But there are a few options that can help save your life. If you know you can safely drive away from the tornado or get to a nearby underground shelter or sturdy building, do that. Do not try and outrun a tornado. Tornadoes can move at over 60 miles an hour, and their path can be unpredictable, with strong winds far from the funnel. This is especially true for semi-trucks. The large surface area of the trailer makes it easier for strong winds to loft the vehicle into the air. If the tornado is about to hit and there's a ditch on the side of the road and deep enough to protect you from flying debris, pull completely off the road. Move away from your vehicle, lie down flat on the ground, and cover your head. If you decide to stay in your car, keep your seatbelt on. Keep the engine running so airbags can deploy. And cover your head. Duck below the windows to protect yourself from blast. Now, admittedly, both of those options are scary, so you might be tempted to park underneath an overpass, but this is not a good idea. Winds accelerate under the overpass, bringing dangerous flying debris. And if you climb higher up the sides of the overpass, you will be exposed to higher winds and more flying debris. They act like missiles. This is what injures and kills people the most in tornadoes. Wood flying around in a tornado can have the same energy as detonating a gram of TNT. And there are thousands of pieces of debris whirling around. So before you hit the road, plan your day around the timing of the storms. Give yourself a buffer to be in or nearby safe shelter, because you want to have the advantage on severe weather days.
That's just a good review. Tornado safety with regards to if you're on the road. If you're in a home, remember with the tornadoes, you need to go into the basement, or if you don't have a basement, go into a room with no windows in the center of the house that's sturdy. Bathrooms work great, and if you have a cast iron tub, you get in the tub and put mattresses over the top. Some basic tornado safety things. When you have stuff outside that can be blown away and act like missiles, like grills, patio furniture, bring it in when the warning is issued. As to how they form, we're not entirely sure. There's not a lot on that. We just know they form off of supercells. Remember those big thunderstorms that move forward. But the biggest part of the exam is going to be focusing on this right here. I'm also going to post a video tonight for everybody, just of another review I did for tornadoes. Okay, we'll move back to here. Okay, some different places, different names of hurricanes around the world. Know a couple of different ones. You know, Ivan, Andrew, some of the stuff like that. And then I'm gonna post, you can answer these questions. You can answer these questions off of the documents I'm going to post tonight for you guys that I mentioned earlier, right? Those are the ones with all the information on the case studies, okay? And let's see, with the 3 hurricanes that have been Category 5 when they made landfall, you will need to look that one up. So look that one up, Google that, super easy. Okay, any questions on hurricanes and tornadoes?
I just had a question about the storm surges. So are storm surges just flooding, pretty much? Is that
Yeah, so think of it this way. There's a big low pressure zone in the eye. That's kind of where it's sucking up all that air.
okay?
And if it's making suction, actually creating a vacuum, it actually pulls the water up a little bit.
Oh,
And so
okay.
that's kind of what does it, is this kind of vacuum effect pulling the water up.
So that's when it hits the land, all that water is
Mhm.
already above and flows on.
Mhm. Yep, exactly. Great question. Any other questions? Okay.
I just wanted to make sure
Mhm.
about if you're doing the whole review, just the volcano again.
Mhm.
I got kind of confused with the viscosity.
Okay, so say it. What is high viscosity?
My viscosity is thick,
That's right.
so it causes a bigger explosion.
That's right. Think of it this way. The thicker viscosity traps more gas. The bubbles
Okay.
can't get out of it as easy. Whereas water, just floats to the top and it's gone. Whereas if it's in maple syrup, it kind of gets stuck in there. And as you add more and more and more bubbles, it builds more and more and more pressure.
Okay. Okay.
Yeah, great question.
Yeah, I just wanted to make sure I got confused.
No, perfect. Any other questions?
No, not for me.
Okay. Well, there's also that other review posted in the announcements from this morning. That's another good one. It's like 2 hours long, so it's a really long one. Hopefully this one is helpful too. I'm going to post some more videos tonight with this recorded one for you guys to watch. And then I'm also going to post this document. So you should have plenty you need to study and prepare for the exam, okay? And if you have any questions, shoot me an email. I'm more than happy to answer. I'll be getting a bunch of grading done, so just watch. That'll get put in. Hopefully, I can get to also some extra credit tomorrow, so you can start seeing test grades bump up and stuff. So it's just been crazy. I'm sorry I'm behind, but I'm also in school in my doing a PhD program. So I'm trying to balance everything and keep it going. But don't worry, grades will be in just fine. You guys will do fine. I know for a fact, both of you guys are going to do just fine. Okay? All right. Well, I'm going to stop the recording. Stop share.